So, our class, we're gonna get started. All right, first, just an announcement about another event coming up. This one, community specific, ASHD annual dinner. So this is, September 27th. So next Tuesday, the day before. But there's more information, so this will be included in the slides, and there's more information about signups available at link. Okay. So today we're going to have YouTube Friday. We're going to go over a few videos illustrating some of the concepts we're talking about this week. And then we're going to discuss boundary conditions and apply what we've learned in an example of application boundary conditions. So these are some of the videos we're going to go over today. It's not a question or comments from one of you, like, should we just skip to review instead of looking at videos? I view this as review. This is material that's part of this class. And we're reviewing it through a different, this would, instead of with slides or with board work, we're reviewing this using videos to illustrate concepts that we discussed in class. I know some of it can be a little silly, but I do view this as another way of looking at the material. And this is part of class, right? So this is part of the material I expect you to read. Okay, so we have a few videos to watch. But mainly, so we've been discussing a lot of different concepts in math, including tensors, divergence, right, results in the principal negative code, say delta b equals 0. You see an illustration of exactly what that means. Lagrangian and Eulerian reference frames, I know it can be a challenging concept, so I'll have some review of that as well. And then a little bit about the Navier-Stokes equations. Again, it's someone else's work instead of just mine. Okay, so we'll start here. So this is a demonstration of what a tensor is. That I think is probably when I saw this is really when I understood exactly what a tensor was. And we'll discuss how it's related to vectors, which is something that we will be using. Hold on one second.
Instead of having 3 components and 3 basis vectors, we now have 9 components and 9 sets of 2 basis vectors. Notice also that the components no longer have a single index, they have 2 indices. Why might we need such a representation? Consider, for example, the forces inside a solid object. Inside that object, you can imagine surfaces whose area vectors point in the x, or in the y, or in the z direction.
So he's illustrating here the concept of the unit normal, right? Something that we discussed and we'll retract fluxes in or out of surface. So this is a surface, right? This little foam dart here can represent the unit normal of that surface. And so that's one of the 2 things that's kept track of within this tensor notation is the unit normal of the surface that force is acting. Right, so that's one of the 2 components of that tensor notation.
And on each of those types of surface, there might be a force that has a component in the x, or in the y, or in the z direction. So to fully characterize all the possible forces on all the possible surfaces, you need 9 components, each with 2 indices referring to basis vectors. So for example, base of XX might refer to the X directed force on a surface whose area vector is in the X direction. Base of YX might refer to the X directed force on a surface whose area vector is in the Y direction, and so on. This combination of 9 components and 9 sets of 2 basis vectors makes this a rank 2 tensor.
So, so it's a little bit more, when we see that tau ij, that's where that comes from. Or that's what it's describing, right? So it's, keeping track of, it's one thing that we can write down, right? Tau ij, that, stress tensor. They keep track of all the shear stresses on, on all the possible faces of the unit cube of a fluid element, acting at all possible directions. So this video also, we want a review of just what a vector is. Then I encourage you to take a look at this video as well. It's longer than we have time to go through all of in this class. But at the start of the video, this introduces a vector as imagine it's having 3 of these cubes together, right? That's how we keep track of the X, Y, and Z components of the volume. And so vector is a rank 1 tensor. You've actually been dealing with tensor calculus every time you deal with vector. But just defining yourself as rank 1. This tau ij has 2 components, right? 2 directions to keep track of, the area as well as the direction of force. So we call it rank 2 tensor. And that's it. I'm not going on to try rank 3 tensors. You can generalize this in more ways. So another concept that we've discussed and come up is that of divergence, right? So we said that the again, the incompressible equation of mass conservation for a fluid is del dot B equals to 0, or divergence of velocity equals to 0. And we looked at my hand-drawn example of we have flux into and out of a small control volume, and we have some acceleration in the X direction, right? So the fluid is traveling faster out of this control volume in the X direction, or out of this point in the X direction, than it entered this control volume. Del dot B equals 0 implies that there had to have been like the material basically that's moving out of here faster, right? There's more material moving out of here in the X direction than came in the X direction. That material has to come from someplace. And we would see that could, for example, come from 2-dimensional flow, deceleration into water. This is just a much better visualization of that same concept. So I'll show this.
Take a look at this vector field, and think each vector is describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness.
I want to be clear, this is a fluid where del dot B is, this is an example where del dot B is not. Right, so right now we're just introducing the general concept of divergence. And so in this example here, we do not yet have del dot B, we have not yet forced the constraint of del dot B, right? And if del dot B is non-zero, then that implies the existence of a source or a sink somewhere. And since from in our mass conservation derivation, we said we're going to have mass conserved. And so for a fluid with constant density, that implies del dot B equals to 0, right? Because there are no sources of sinks, strength sources of sinks, it's 0.
Del dot B equals 0 with you have a source and a sink that equal constraints.
So del dot B could equal 0 if you have a source or a sink at equal strength located at the exact same point within the fluid, say that fluid. Okay, because this holds the whole every, so when we say this, right, we're writing differential equations, they hold everywhere within the fluid. And so if you have a source at one point and sink at another point, globally mass will be conserved, locally mass. Okay, this is saying mass is conserved everywhere, at every source. Okay, yeah. Again, not complicating this example, but this is just illustrating what the divergence is. All right.
Tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field evaluated all of those points that act as sources will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it from another direction. So that would still insinuate a certain spontaneous generation. Now, on the flip side, if in a small region around a point, there seems to be more fluid going into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out three-dimensional outputs. The divergence of that vector field is a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. And purposely delaying discussion of computations here, the understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one, used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems.
So this is an example of a vector field where if b is equal to 0, right? So it doesn't apply to the velocity is just 0 or unchanging everywhere. It's just that if there is a change, for example, in x, then it's balanced with three-dimensional flow by a change in velocity. That makes sense? Okay, this is one of the key equations, right, in our full expression of agriculture, right? Yeah. So they'll not be all is equal to 0 if the fluid is they'll let be always equal to 0 if fluid is incompressible. Any questions on this? Thanks. All right, so I know another sticking point are Eulerian and Lagrangian coordinate systems, right? So we discussed the how we keep track of the acceleration of a fluid particle, right? We write that down total derivative. And this so these are some illustrations of what that really means that come from the National Committee on Fluid Mechanics films, which are old, but pretty great for their illustrations of different concepts of fluid mechanics.
In addition to moving from place to place, an elementary piece of fluid is generally squeezed or stretched and rotated as it goes. We are going to focus our attention on the translation, not on the deformation. In this flow of water through a contraction, hydrogen bubbles have been used to identify pieces of fluid so that we can follow their motion.
It's more or less what we were drawing, what I was drawing out on the slide to illustrate the concept of steady state flow, but fluid particles typically exhibit acceleration. You can see it here. You're looking for. So this is, you see this flow through this contraction. This is steady state, right? As in from our lab reference frame, as we're watching this flow is unchanged, right? The velocity field that we see here is the same throughout the course of this illustration. But we know by mass conservation that the area here is larger than the area here. Meaning the velocity of this outlet here has to be larger, right? When the area is smaller, the velocity is larger than the velocity coming in, right? To conserve mass. And therefore, a fluid parcel, we just look at this little square here, has to accelerate as it moves up and through this end. It's going from low velocity to high velocity. So we know steady state in the Eulerian frame of reference, if we're watching this, velocity field is the same over time. Individual fluid particles exhibit an acceleration. Right, so that's the convective derivative term of the total derivative. And so I just want you to watch for that as you go back a seconds. So you can see that.
Been used to identify pieces of fluid so that we can follow their
Take
motion.
one and just follow it.
These pieces are quite large, however, and we would like to examine the motion of very small, infinitesimal bits of fluid. Therefore, it will be more convenient to have a computer simulate these motions and generate the visual displays for us. We will use open circles, as we are doing here, to identify material points. In elementary mechanics, we are accustomed to describing the position of a material point as a function of time, using a vector drawn from some arbitrary initial location to indicate the displacement. We will use
So later in this video, we've actually discussed the how we can see the acceleration of the fluid at different points. I just want to show that.
but we can also show the material derivative of the vector field directly. Here are two laboratory points infinitesimally close to one another in a magnified view of an arbitrary steady flow. They lie on the same path line, and the material point is traveling from one to the other. The velocity of the material point is indicated by an open arrow attached to it. Clearly, although the flow is steady in the laboratory frame, the moving material point experiences change as it.
So this could be, 2 points within that convergence spread that we just saw, where it's wider at the start and narrower at the beginning, right? So the flow here, if we're looking at right along where that flow is converging, imagine we have those 2 points sitting within that flow.
Travels to regions where the steady velocity is different. The total change will be the difference between the velocities at the two laboratory points, indicated by the solid Eulerian vector.
So if this is the velocity of the particle at this first time, right, we'll call it T0. And this is the velocity of the particle the second time, right? We'll call that T1. We can see the acceleration here in two ways. So the first is that the length of this vector here is larger, right? We can think of that as in that converging flow. We got a smaller area, and therefore there is a higher velocity at the exit. And therefore the magnitude of this is larger. But except remember, velocity is a vector, right? So when we say acceleration, a change in the direction is also an acceleration. It also requires an applied force. And we can see here that this vector has also changed direction, right? So there is acceleration in both x and y as this fluid particle moves. We notice steady flow. There is that acceleration on the fluid particle. All right, last example. Refresh to get the right points. So we've also discussed the Navier-Stokes equations. And with this, partly because this guy's enthusiasm in having your studies is, it's quite extensive. But we also have, I think, a good discussion of what the Niagara Stoke equations are here. It's phenomenal work. And we'll see if he makes a mistake in his discussion. We're gonna go over it as well.
There's a number on the ribs as well, the pain of the ribs, like, but I'm gonna say this is complete commitment to Navi States and Freedom Camp. Why did you do that? What are the Navi States? The first one, grad.u equals dot, and the second one, rho u by t equals minus square p plus mu plus square u. That's right. It's like those mathematical equations, they look quite scarce, but they're actually universal laws of physics. So this is why these guys model every single fluid you have on Earth. And I mean every fluid. Put a fluid in your head. These guys.
No question for you. That's true. Why not? Ketchup is non-Newtonian, right? So, yeah, so this is not in fact model every single fluid you have on Earth. Yeah, what's up? You know, so, the not in fact model every single fluid on Earth. But every Newtonian fluid on Earth, which accounts for a great majority of what your life is. Wouldn't lava not be Newtonian? I would guess it's not Newtonian, but I'm not positive, to be honest. Yeah, it's not a lava thing. But that it's quite rock, right? It looks like rock, yeah, but it's, I mean, it could be native Newtonian, right? As a little quite rock, it could be native Newtonian. The question is whether or not it has a conflict. Yeah, sorry, was there another comment or question? Okay.
What goes on the fluid. I tend to think of it as something which changes shape to match the container that it is. Of course, a liquid, but also a gas, even some solids. So like ice, you think about a glacier flowing down a mountain, you watch those time-lapse videos, it kind of looks like a river. So ice in that sense behaves like a fluid. It's changing its shape to fit the valley, the glacial valley, which is flowing. So the first one, this is literally just saying that mass is conserved. So this is just saying I have some blob of fluid, it moves around, you know, with some velocity, it maybe changes shape. I'm not adding anything, I'm not removing anything. I would want the same mass of fluid to still be there. Mass is conserved. It's a pretty standard law of physics, it's a lot of sense. This guy is just Newton's second law. So this is telling us that mass times acceleration is false. The top one tends to be the mass equation, conservation of mass, or the incompressibility equation, and the second one is the momentum equation.
Momentum equation for force. So you'll notice here there's a couple things. One, these denoting vectors is under bar, right? They're over bar, that's fine. There's also this rho hat. So he's accounting for sort of other forces that may be acting on the fluid in this rho hat. We have ignored, I guess our rho hat, all we have is gravitation. But gravitational force. All right, and then I'll just point your attention to this, which is on the slides. If you're interested in learning more about the Millennium Prize, there's a discussion of what exactly the Millennium Prize entails at the end of this. All right, any questions on any of that before we move back? Yeah. I looked at the lava, it is not going to be true. Lava is not going to, is it shear thickening or shear thinning? Unclear. Okay, thank you. So therefore, lava would not be modeled by Newton.
I would note, it says the reason for this is the formation of construction of crystal networks during the shear.
The formation and construction of crystal networks during each year. Yeah, that's really big. Yeah, that's really big. Okay. All right. So, and then if you are looking for more, so this is that Millennium Prize bit. Looking for more information on Lagrangian and Eulerian control line. Didn't look at this video, but it is on the slides and has a brief discussion of Eulerian and Lagrangian control line. for, our boundary conditions, right? So we were discussing, so we developed equations for, map, and energy balance, that are differential equations. But now to actually use these, we need to know initial and boundary conditions, right? Which is where we left off. So, if it's unsteady, we need to know the value of all the variables that's equal to 0. And we also, in general, need to know the velocity at each boundary, right? Just like in heat transfer, I know you're spending a lot of time probably discussing boundary conditions. Boundary conditions matter quite a bit here as well. So, we're often going to be assuming that we have a Newtonian fluid that's incompressible and has constant properties. It's a pretty common case to examine. So it wouldn't apply for lava or ketchup, but would apply for water flowing in a river, air flowing through, oil flowing through a pipe. And so in this case, we obtained state review. We saw just a second ago, del dot D is equal to 0. Rho times the total derivative of velocity equal to rho g minus grad p plus d del squared p. Remember, right? This is F equals ma, right? But applied to an individual fluid parcel as it moves through our or moves through our system. And then for a incompressible flow, incompressible Newtonian flow with constant properties, we have this form of the energy balance from the end of our energy balance. And now, if you look at this, this is really the only, we have the main variable here is T, temperature of the fluid at each individual point. And we have the velocity of the fluid coming in here and giving rise to that distance dissipation. Yeah.
That DPT is faculty.
That's big apple. That's right. Yep, that's fair. Yeah, we don't break. Sorry about that. So in this kind of flow, you'll notice that velocity occurs down here, right, in the speed term, right? This is the term, but temperature doesn't appear up here. Right, so if we assume constant properties, we could, for example, look up our viscosity for a given temperature. And so there's no temperature dependence up here. Right? We're not letting temperature vary, or the variation in temperature in space doesn't affect what's going on. So for this kind of problem, you typically just solve first for velocity and pressure. You can have your Stokes, and then figure out what's going on with your two. So this is where, let's say we're mostly going to leave the temperature part of this for heat transfer in this. And we're going to, for incompressible flow with constant properties, we're generally going to be confining ourselves to just an energy source. So let's discuss the boundary conditions. So I want to discuss boundary conditions for the velocity and the pressure that we're often going to see, the types of boundary conditions that we might see. Right. So to solve these expressions, we need boundary and initial conditions for velocity and pressure. Initial conditions is just what those things are at t equals to 0. But there are a number of different types of boundaries that you can encounter. Both in terms of analytical solutions to the Navier-Stokes equations, and also when you're doing CFD. There are a number when you open up the CFD solver fluents and you're trying to solve, or you're walking through the tutorial to solve, for example, the first part of the CFD project in this class. You'll see many options for different boundary conditions. We'll talk about some of the common. Because in general, like if you think about it, we discuss what happens on a wall, right? So on a wall, we have a wall or a solid surface, we have no slip condition, meaning the velocity of the fluid equals the velocity of the wall. But we can also have, for example, the interface between a liquid and a gas. that. For general flow and outflow boundary conditions, as well. One common boundary condition is that it's a solid surface, right? So we can write the no slip condition, we often write it as E equals 0, right? That's only true if the ball is not moving. If the ball is moving at a velocity of 0, then the no slip condition is V is equal to 0 at the wall. More generally, no slip implies that the velocity of the fluid is equal to the velocity of the wall where it meets the wall. So if this table were moving in our lab reference frame, then the fluid immediately adjacent to the surface of the table would be moving at the velocity of that fluid. So we'll often have, especially in CFD, like if we're modeling a we're modeling flow through a wind tunnel or something, we'll often have an inlet or outlet condition. We'll have to describe the velocity and pressure at those. Sorry, go ahead. So how often is the no slip condition not true? How often is the no slip condition not true? Practically never. It's practically always true. I mean, the exceptions are fairly exotic things like water passing through a carbon nanotube. And water passing through a carbon nanotube has to go more or less 1 molecule at a time before it happens. Yeah, effectively, it's whatever. Effectively. Effectively. So and we're going to assume it's true, or we're assuming it's true. We're not going to look at this. And so in our outlet, you typically have some known velocity and pressure, or some known velocity pressure distribution that you impose on the system. And again, this is if we were doing a CFD of flow through this region here. That's a very common boundary condition that you would use at the beginning or end of your. Another important one though is that the free surface of a liquid, right? So by free surface, I mean where the liquid interfaces a gas. And the real key concept here is that a gas typically has a much lower viscosity than a liquid. Right? Air has a much lower viscosity than water. And so that implies that the gas does not put up much resistance if the liquid beneath it. So that gives us a boundary condition that we're going to use at a free surface. So first, we typically have pressure equal to the pressure atmosphere. And then we'll have omega is dA to dt. Sorry, W is equal to dA to dt. So we'll say that the velocity, the z component of velocity, is equal to the velocity of this surface. The rate of change of height of the surface. Going to be the velocity, z component of velocity of this interface that is variable represents. So z surface with this eta x, y, we're saying we're going to allow the surface to move up and down. If the surface is moving down, for example, so it makes sense of this. If the surface is moving down, then the fluid just inside that surface also, that means the fluid inside that surface is moving down. And therefore, the z component of velocity is just the rate at which the height is changing. Sorry, throw another layer. And then that's no shear stress at the surface. So this comes from the fact that the viscosities are very different. And basically the gas, because it has this low viscosity, it simply cannot produce a shear stress force on the fluid itself. And so this implies that the derivative of the velocity with respect to z is equal to 0. Remember the shear stress we have the shear stress based on this rate of change in velocity. HC would be here. dP is basically saying that shear stress is 0 at 3. So this is a boundary condition now in terms of the derivative, right? Instead of in terms of just the value of the thing. But this is a perfectly valid boundary. Yeah.
Sure, the new Greek letter, what exactly that?
Yeah, so, we could write, I guess we could have written this H or something, I probably would have written this H. So this is the, this is the, height of the two surfaces. Eta is the height of the two surfaces, right? C surface is equal to eta of x, y. So you can rewrite this as W, the C component of velocity, is equal to the partial derivative of C surface. Make more sense? Yeah, I know, yeah, but most systems do this time of day. So C surface is that. Okay. Okay. All right, so I want to look at just an application of this. Remember, one of the things that we discussed not too long ago is that there are often multiple solution paths to get the same problem. This is essentially going to be an illustration of that. So we'll look at wet flow between flat plates, where so this is an example where we have the upper plate moving and the lower plate fixed. We kind of did a hand waving derivation to get to this velocity profile when we defined viscosity. But now I want to show or I just want to walk you through a more rigorous derivation. This is simply starting from and in your first homework post exam, you'll do a similar kind of derivation for pressure driven flow. And essentially follow along. So the setup here is that we have upper plate moving at some known velocity v and a lower plate fixed. And we're going to say that there's no pressure gradients, there's no driving pressure in this system. So it's not, we're not applying pressure across the system in order to make fluid move. We just have that velocity plate kind of make the fluid move. And we'll assume steady state. So this upper plate is not accelerating. The question is, what is the velocity? Well, what is the velocity profile between these two plates? So we showed it was linear, right? In one of those early classes, show that we should see a linear velocity profile. But I want to walk through using the Navier-Stokes equation to get to the same place. Right, so this will be an illustration of how we can take the Navier-Stokes equation, all their terms, and figure out which ones cancel out and which ones drop out, in order to figure out something about this. Sorry, your question about. Oh, never mind. Choose you. So we'll start with Navier-Stokes. So we have del dot E equals 0, rho times the total derivative of velocity vector time, rho g minus del minus grad p plus mu del squared. Those forgot my animation to work this. So so continuity is generally, or mass conservation is generally going to be a good place to start. If you're at a loss of where to begin. Mass conservation, let's see what mass conservation tells you. So we're going to start with mass conservation theory. So mass conservation, we write as for a incompressible fluid, we write del dot B equals 0. This is what that looks like expanded. So UDS plus PDY, WDC. So in this case, we assume that the plates are infinitely long and wide, then there should be no change in the x component, which is evenly long, or the z component, which is evenly long. So the rate of change with respect to x, the rate of change with respect to y, z, is 0. So look at this expression, it means this thing is 0. Wdx is 0. WdC is 0. And we're left with, sorry, this should be, yeah, dy is 0. Actually, we have a couple of things. So this implies that du dx, this is still true. Which means that u is not a function. One can get it. But we also are left with that dy is 0. Right? Meaning that the velocity is not changing the y. So if we solve for the y component of velocity, example by integrating dy equals 0, we'll do that. So if we have d dy equals 0, what does this tell us? Is the y velocity component? B is equal to, reiterate this, some constant. All right, so B is equal to some constant. And if we know, for example, the velocity is equal to 0, the y component of velocity is equal to 0 at the bottom plate, then this is telling us that y component of velocity is 0 here. So this allows us to then solve for the y component of velocity. So B is equal to 0. Yes. Yeah, so how is it that you see a lot? So this is the x component of velocity, which is non-zero and varying. So this is the x component, yes, this is the x direct. So the velocity is not changing, this velocity profile is not changing. So this is, so yeah, so this is how we illustrate, or how we would typically draw what the velocity profile is. When we like have this line here, what we're saying is we're drawing the velocity profile at this point where this line is. And now we're saying that the velocity in the x direction is increasing with y. That's what this represents. This represents the velocity profile and what it looks like as a function of the y. This is how we just draw. This condition implies that no matter where we draw this line, we would have the same velocity profile, right? But yeah, this is showing the velocity profile. So yes, so that this condition implies that along some horizontal line, we're looking at the center line here, right? The x component of velocity u is the same everywhere along this. It doesn't vary in x; it only varies in y. But the dy is not equal to 0. We could have a situation where it goes up a little bit, also like it could go up a lot more, right? Where the velocity gets changed linearly, but it's on the y. Yeah, if this condition were not true, if the dy were not equal to 0, I'll just say it would be very long. But yeah, it would. If dy were not equal to 0, actually by continuity would imply that du dx would have to be non-zero for two-dimensional flow, right? Continuity. If this thing were not 0, let's say w is 0, it's 2d. If this is non-zero, then this would have to balance it out for mathematical sort of, right? So we would have, so that you would get this case, yeah.
So isn't that second equation multiplied by velocity?
Second equation This is saying that all derivatives in X, all the particles with respect to X. are zero. All the second,
Right up, yeah.
no, this is what delta V is equal to zero resolves. Yeah, this is the definition of delta V equals zero.
The velocity from the wing, or if the top plate was accelerating, that velocity go up the curve.
Top plate we're accelerating, yes, that's a velocity profile. Yeah. Okay. So now let's look at the X momentum balance. So this is what we start with, right? From the Navier-Stokes equation, we've written this out on slide before, it's in your textbook as well. And there's a lot of terms, right? So where should we start? What do we do first? All the X. We know all the X's, so start canceling things out, right? We're gonna apply what we know, we're gonna start canceling things, right? That's generally where, okay. So we know it's a Newtonian incompressible fluid. So we can write this, we know that this holds, but now we're gonna start canceling things out. So gravity in this case is in the y direction, right? Let's say y is pointing up, gravity is going in the y direction. So g sub x is 0, so we drop out that first term. We assume that there was no pressure gradient in x. So there's no change in pressure in x, so that dx is equal to 0 in this problem. Not the pressure driven flow problem, but in this problem, dx is 0. We said that u is equal to u of y only. Right, so the second derivative of u with respect to x has to be 0. And as well as the second derivative with respect to t. We said that it's steady state, right? So the partial of u with respect to time is 0. We said u is equal to, again, just u of y. So du dx is equal to 0. And v is equal to w is equal to 0. Plates are very wide and long. We don't have any other flows in the problem. The only thing going on, everything is just moving in the x direction. W and v are also 0. Almost everything is canceled out. We have one term left. All right. This u squared u dy squared. So we can now integrate this, right? We end up first du dy is equal to some constant plus c1, and u is equal to c1 y plus c2 after we integrate it second. Now, how do we find C1 and C2? Boundary conditions, right? And now this is when we need those boundary conditions to apply. Okay. And our boundary conditions are no slip, right? The velocity is equal to 0, bottom plate is not moving, the velocity of the bottom plate is moving. And the velocity in the x direction is equal to that capital V in the at the upper plate. We have u is equal to c1 y plus c2. Now we apply the boundary conditions. We'll say that u of minus h is equal to 0, u of plus h is equal to that velocity v. But bottom, right, plugging this in, we get 0 equal to c1 times minus h plus c2. So c2 is equal to c1h. Upper plate. V is C1H plus C2. Plug this in. And we have an expression for C2 with C1H. So V is equal to C1H plus C1H. Or C1 is V over 2H, and C2 is V over 2. So we can solve for this velocity profile as V over 2H times Y plus V. One thing I want to take away from this, all right, so again, the importance of boundary conditions, right, rapidly solving this velocity profile. But also when you see the Navier-Stokes equations, it looks like impossible, right? But for the cases that we're going to consider in this class, almost everything is gonna be thrown out. So, it's not a